All right. Well, we're into chapter 4, and we're looking at reactions in aqueous solutions. This chapter is all about reactions in aqueous solutions. So, in order to get started, we want to look at a few terms. So, just get these terms down so that everybody is familiar with them. A solution, we've seen this definition before, but a solution is a homogeneous mixture of two or more pure substances. As long as the mixture is uniform throughout, that is going to count as a solution. A solvent is the substance that's there in the greatest amount. Now, that is sort of a working definition. You can sometimes have the solvent be there in a lesser amount. That is unusual, but it can happen. So, usually the solvent is there in a greatest abundance. Anything else, we're going to call the solutes. So any other substance we will call the solute. And then finally, we want to look at this word. Aqueous solution is simply a solution that is where water is the solvent. And just a quick note on the pronunciation of aqueous. I sometimes hear the word aqueous, aqueous, and aqueous. And for whatever reason, when I learned chemistry, I learned aqueous, and I don't know if that's a regional difference or whatever, but it doesn't really matter. Okay, so we want to talk a few minutes about something that we call electrolytes versus non-electrolytes. First things first, water itself is not an electrolyte. If you were to take an electric circuit, so like here we've got this light bulb, if you were to take an electric circuit and run it through the water, so the only way to complete the circuit is for electricity to flow through that water. Well, we'll find that water, and I should specify here, pure water is not a good conductor of electricity. Now, before you run off and go look at your parents and say, hey, you told me my whole life that water will conduct electricity. Well, it will if it's the water out of your tap. But pure water is not a good conductor of electricity. We will find that tap water and even pretty good bottled water are going to have electrolytes in them. In fact, it makes the water taste better to have a little bit of some electrolytes in them. So if you were to have absolutely pure water, let's say you got a bathtub that was perfectly clean and you filled it up, you would find that the water would not be a good conductor of electricity. But as soon as you stick your foot in there, salts from your skin are going to cause it to become a good conductor of electricity. So it doesn't take a whole lot to make it conduct electricity, at least a little bit. So don't go stand in the shower with the hairdryer just because I said this. I am specifically warning you, do not stand in water while using electric devices. Okay, now that we got that public service announcement out of the way, let's look at what happens when we put sugar into the water. So sucrose is just regular table sugar. That's the sugar that you maybe put in your coffee or something. And sucrose, we will find, is not an electrolyte. Now, what that means for practical purposes is that it's not an ionic compound, and if we dissolve it in water, it will not conduct electricity. So sucrose is not an electrolyte, or a non-electrolyte if we want to call it that. However, if instead we take that same solution and we put salt into it, well, the salt will dissolve pretty easily, and once those ions are present, we will find that solution will become a good conductor of electricity. So, it turns out salt is a good electrolyte. So we want to find what kinds of things are good electrolytes and what does this mean that something is an electrolyte, and why is it that ionic compounds, as we'll see, are good conductors of electricity. So let's look at what happens when an ionic compound dissolves versus when a non-ionic compound dissolves. So here I've got a picture. This is from your textbook. And you'll see here that we've got sodium chloride. That sodium chloride has... the sodium chloride is made up, obviously, of sodium ions and chloride ions. And before it dissolves in water, it is in a crystal. and the oppositely charged particles are attracted to each other. And when you dissolve it, what happens is the water molecules will start running into that crystal, and some of the ions will get surrounded by the water molecules. And when they do, we say that they have been solvated. And so these ions get solvated by the water molecules. Well, once the ions are surrounded by water molecules, they are completely capable of dissociating. In fact, that means that they can move around independent of each other. That allows for charge to flow through the solution. Now, normally when we have electricity flowing through something, it's the electrons that are flowing. But in the case of an electrolyte solution, we'll find that it is the ions that are flowing, not the electrons by themselves. So it is the ions that are flowing. Over here on the right, we've got methanol, and methanol is CH3OH, and it has all covalent bonds. There are no ionic bonds here, and it does not dissociate. It does not turn into ions and dissociate. So it turns out methanol is not an electrolyte. It's a non-electrolyte. So electrolytes happen when you have ions that are present in solution, and those ions can move about freely. Non-electrolytes do not form the ions and therefore are not good conductors of electricity. So in the process of dissolution, and I talked about this a second ago, whenever you have water molecules that surround an ion, we say that the ion has been solvated. So here we've got a solvated chloride ion, there is a solvated sodium ion, and then there's several others. Not all of the water is going to be solvating. Some of the water will just be moving around. But once those ions are solvated, they are said to be dissociated, and it undergoes the process of dissociation. And we will find that the ions can move freely, and that's why it conducts electricity. So we want to look at number 15 on the in-class assignment. So we're going to switch over here to our in-class document camera, our assignment camera. And here it has specify what ions are present in solution when each of the following strong electrolytes dissociate in water. So when this happens, all I'm looking for on this particular problem is what are the ions that are present. And really all you need to know is what is the ion and what's the charge on it. You don't even have to know the number of ions, you just need to know the correct ion. Although the number of ions is pretty easy. So zinc, well, we know chloride has a -1 charge. So we'll go ahead and put the chloride over here. And that means the zinc must be 2+. Now, you'll remember from previously that zinc here, we got zinc 2+. Zinc is always 2+ when it is in solution. So in case we didn't know that, we know that now. What we have here is nitric acid. Nitric acid is on the list of what we refer to as strong acids. And when strong acids dissociate in water, when they dissociate, we're going to get the hydrogen ion and whatever else is left. In this case, it'll be the nitrate ion. So hydrogen ion and the nitrate ion. When we look at other acids, we will see that we get those particular ions as well. Here we've got ammonium sulfate. Our cation, our positively charged particles, are ammonium ions, so NH4+, and our anions are sulfate, SO4 2-. So SO4 2-. All right, for this one is potassium acetate, and again, this is really helpful if you know your ions. You'll be much better at this if you know your polyatomic ions. All right, so potassium is K+, and acetate is just simply C2H3O2-, and that is the anion. All right, over here we've got aluminum nitrate. Aluminum is in group 3. We know it forms a +3 charge, and nitrate, as I'm sure you have memorized, is NO3 minus. All right, so that is all of those. That is just practice on figuring out what ions are present. We're going to be doing that quite a bit as we look at additional problems. So we want to distinguish between what we call strong electrolytes and weak electrolytes. So strong electrolytes are things that when they are dissolved in water, they completely dissociate. And by completely, we mean essentially 100%. Now, if you go on and take the second semester of this class, you will see that in fact, we do sometimes have things that dissociate like 99%, and we're going to call that a strong electrolyte. Maybe even 95% we would call a strong electrolyte. But something that dissociates 1%, we're not really going to call that a strong electrolyte. We will find that things that are considered strong electrolytes in this book and in this chapter are going to include soluble ionic compounds. And I have a list of rules, solubility rules, that you can look at, and I'll show those to you here in just a bit. That will help you to know which ions are the soluble ionic compounds. Strong acids. Strong acids are acids that when you put them into water, they dissociate 100%. And there is a list of strong acids that I'm going to ask you to memorize. We'll get to that a little bit later. We have strong bases. Strong bases are, again, I have a list of strong bases that I want you to memorize. They dissociate essentially 100%. So soluble ionic compounds, strong acids, and strong bases. Weak electrolytes, on the other hand, when we put them into water, they only dissociate partially. And that will include things like weak acids and weak bases. And we'll find that some ionic compounds, when we put them into water, they don't dissolve very well. And so we'll consider those to be weak electrolytes as well. So in this next section, we want to look at what we call precipitation reactions. And precipitation reactions are when we've got, we put two solutions together. Each of the solutions has no solid in it. As you look up here, this one is a solution. There's no solid in there. Same thing here. But when you start to mix them together, you get a precipitate. You get a solid. So that is called a precipitation reaction. The particular reaction that is going on here is between potassium iodide. So potassium iodide is up here in solution. You'll see it's even colorless. And lead nitrate, lead 2 nitrate to be specific. And the lead nitrate is also colorless. Now, it does not necessarily have to be colorless in order for it to count as a solution. It just has to not have solid in it. When we mix them together, we'll find that some of the ions really like forming a solid. And the ions that form a solid here are lead 2 and the iodide ions, and we'll get PbI2, and that's what this yellow solid is. Now, sometimes people look at this picture and they say, that doesn't look like a solid, it looks like a liquid. Well, it's actually just fine particles, so very fine powder of lead iodide, so lead 2 iodide. And so what you'll find is that once you let that reaction settle, that you'll get a solid powder that is at the bottom of the flask. We'll find that the other ions, the nitrate and the potassium ions, they stay in solution. So they're still floating around in solution. So this is a precipitation reaction. I want you to be able to predict precipitation reaction. So if I want you to be able to predict these reactions. If I were to give you two solutions and give you the solubility rules, then I would want you to be able to tell me, are we going to get a precipitate or not? So let's look at the solubility rules. Now on eCampus, under the lectures folder, you will find a list of solubility rules. I encourage you to look at those quite a bit, but we're going to look at them here on the screen. So the way this works, I've got these grouped into 3 different categories. The first category, if your compound contains these ions, then it almost certainly is soluble. We're going to say it's always soluble, but we're going to say almost certainly soluble. And by soluble, we need to have a definition by what we mean by that. So by soluble, we mean that it will dissolve to at least 0.1 moles per liter, or 0.1 molar. So you'll get at least that amount of solubility. Now, it might be 0.10 exactly, and that's it. And anything over that, it starts to form a precipitate, but that counts. So 0.1, we're going to consider soluble. You'll see the other 2 categories here, slightly soluble. Well, here I'll do insoluble. Insoluble means that it has a solubility less than 0.01, so that's 1/10 the concentration of this other one. And slightly soluble means it's right on the edge. It's in between the soluble and insoluble, and sometimes these can be a little bit tricky. And I will point out a couple of those here in just a few minutes. So these ions are always soluble. Includes group 1, lithium, sodium, potassium, rubidium, and cesium ion. Ammonium ion, so compounds with ammonium ion, are going to be soluble. Nitrate ions and acetate ions. So compounds that contain any of these ions are going to be soluble. We'll find that these ions, compounds that contain these ions, are usually soluble. Now, that doesn't mean always, but it just means usually soluble. So chlorides, bromides, and iodides, those are all in group 7. You'll notice fluoride is not on this list. Fluoride, there's a lot more compounds that are not soluble with fluoride than there are with the other ones. So we don't put fluoride on the list. That's one usually you just have to look up. So fluorides are kind of tricky. Sulfates are usually soluble. However, for this list, I have a few exceptions that I want you to be able to recognize. And these are the exceptions. So for chloride, we have silver ion, mercury 1. This is not to be confused with mercury 2. Mercury 2, where it's just Hg2+. That one, the chloride is soluble, but mercury 1, it is insoluble. Copper 1 chloride, insoluble. And lead 2+ chloride, so lead 2 chloride, is slightly soluble. It means it's in this range between 0.1 and 0.01 as far as its solubility, and that it's kind of, sometimes it's hard to see. Often if you put a chloride and lead 2 together, you'll get a little bit of cloudiness is what you'll observe with that. For bromides, we have exactly the same list, so chlorides and bromides behave very, very similarly. Iodides also behave similarly, except for the lead 2 is just insoluble. In fact, that yellow compound you saw a few slides ago, that was lead 2 iodide. All right, and then next we've got sulfates. So silver sulfate we'll find is slightly soluble. It's kind of on the edge. Sometimes you'll see a precipitate, sometimes you won't. Mercury 1 is just going to be insoluble. Lead 2 sulfate will be insoluble. And then we'll find these 3 ions that are in group 2 are going to be insoluble. So calcium, strontium, and barium sulfate, those will be insoluble. Interestingly, if you look at magnesium sulfate, and I'm going to switch over just real quick to our document camera here. So calcium, strontium, and barium are insoluble, but magnesium sulfate is soluble. So just kind of a curiosity there. All right. Now, the next part of this list, these are ions that are usually insoluble. So sulfides, carbonates, phosphates, and hydroxides. Most of the time, if you have ionic compounds that contain these, they are insoluble. The exceptions, though, are going to include, well, of course, these things that are up here. All right, so group 1s are exceptions, and ammonium salts are exceptions. And then for sulfides, we'll find that, again, those 3 that are in group the calcium, strontium, and barium ions, they are soluble. So calcium sulfide, strontium sulfide, and barium sulfide are quite soluble. For carbonates, we really don't have many exceptions except for the two normal exceptions, so group 1 and ammonium. And then for phosphate, group 1 also and ammonium. For hydroxide, we'll also have the group 1 ammonium. That's a little complicated. I'll talk about that later, but ammonium hydroxide is soluble. But then we'll also find that calcium hydroxide, strontium hydroxide, and barium hydroxide are soluble. So with this list, we want to look at these solubility rules, and it just so happens here I've got this. So here is the PDF that you can get on eCampus. You can download this and print it off, and you will see here that it's got all the rules that I just described. All right, and I have put that on there so we can look at the document and at this at the same time. All right, so all right, I'm just making sure I can do that. All right, so here let's look at number 19 and determine if these things are soluble or insoluble. So here we've got silver chloride. Well, always check the always soluble list first. And our always soluble list, we don't have anything in silver chloride that is on the always soluble list. So these things over here on the always soluble list, that top part, they are not, they don't apply. Chlorides are usually soluble. So if we look here, our chlorides are usually soluble, but silver is an exception. So that means that this compound is insoluble. All right, so if it's over here in the usually soluble, that means it will dissolve. If it's in the exceptions, that means it won't dissolve. In other words, it will be insoluble. All right, let's look at nickel chloride here. So nickel chloride, again, we're looking at chlorides. Chlorides are usually soluble. If we come over here to our list of exceptions, we will see that nickel is not an exception. So that means that nickel 2 chloride should be soluble. All right, here we've got silver sulfide. Well, we'll see that nothing from the always soluble, nothing from the usually soluble. And when we come down here, we'll see that sulfides are usually insoluble. We'll look at our exceptions, and for our exceptions, we will find that silver is not an exception. So silver sulfide is going to be insoluble. All right, next we've got cesium phosphate. Well, if we come back over here and we look, we'll see cesium right here is in the always soluble list. So that means that this should be soluble. All right, strontium carbonate. We'll come back over here. We'll see that carbonates are usually insoluble, and strontium is not an exception. So that is going to be insoluble. All right, lead sulfate. Sulfates are usually soluble. However, lead 2 is an exception. So this one is going to be insoluble. All right, and then finally on this list, we've got barium phosphate. So barium phosphate right here. If we come over here, phosphates, as we can see, phosphates are usually insoluble, and barium is not an exception. So that is going to be insoluble. Okay. So now that we've done that, let's look at our next thing, which is looking at exchange, or what we call metathesis reactions. So exchange or metathesis reactions. Metathesis is the old word that is that's been commonly used, but we can look at this as just an exchange reaction. I often will use the word metathesis because that is how I learned to say it. So the precipitation of lead iodide is an example of a metathesis reaction. This is the reaction I showed you a few minutes ago where we had the yellow solid that formed in the beaker. All right. And what appears to happen here is that the cation of one compound ends up with the anion of the other compound. So lead ion ends up with the iodide ion in the other compound, and we form a solid. And so since the cation and anion, they switch partners, that's why we call it an exchange reaction or metathesis reaction. All right. We'll find that there are three major driving forces for these metathesis reactions. They include precipitation, which is what this section is about, the formation of a weak or non-electrolyte, which we'll see in the next section when we talk about acids and bases, and the formation of a gas, which we'll see in a later section when we talk about gas formation. All right, so let's look at solution chemistry. We have some words that I want you to get down and that I want you to understand clearly. All right, so we're going to be looking at molecular equations, complete ionic equations, and net ionic equations. And the whole reason that we're looking at these is that they tell us slightly different things. Molecular equations tell us what we started with and what we end with. All right, so it doesn't really tell us about what's in solution at any given time. It simply tells us what compounds we started with and what compounds we ended up with. The complete ionic equation tells a little bit more of the story in that it tells us what ions are in solution both before and after the reaction. The net ionic equation only tells us what changes. So when we're doing these kinds of equations, the very first thing we want to do is to write a molecular equation, and it has to be balanced. You must have a balanced chemical or balanced molecular equation before you can move on. A common mistake is that you start writing the equation and it doesn't look balanced, and so you make the wrong formula to make it balanced. Well, that's a good way to get everything wrong. So you make sure you do your formulas correctly. So write a balanced molecular equation. Next, we want to dissociate all things that are strong electrolytes. All right, so dissociate all strong electrolytes. Okay. We want to cross out any unchanged species. So when we dissociate the strong electrolytes, that's going to give us the complete ionic equation. When we cross out the unchanged species and rewrite the equation, that's going to give us the net ionic equation. So those are the steps for doing these equations. We're going to go through this multiple times, so you're going to get good at it, whether you like it or not. So let's move forward. So let's start with the molecular equation. So here I've got a balanced molecular equation that I've given you, and you'll see that that we've got silver nitrate plus potassium chloride, and it gives us silver chloride, the AgCl, which is the solid, plus potassium nitrate. So it treats these as molecules. Even though they're ionic compounds, this equation kind of treats them as molecules. So you simply use the chemical formulas to indicate what species are completely, without indicating which species are completely dissociated. You absolutely positively have to have a balanced equation before you can move on. So we're going to look at problem number 22. And like what we did a few minutes ago, I'm going to go to that split screen. All right, when we look at 22, that way we have our solubility rules available to us. All right, so identify the precipitate, if any, that forms when the following solutions are mixed. Okay, usually what I like to do is to identify what ions are present. So this is nickel nitrate. Nitrate's -1, so that means that nickel has to be nickel 2. For nitrate, nitrate is the NO3 minus. And then here we've got sodium ion and hydroxide ion. So those are all the ions that are present in this solution when we start. Okay, so now we want to see, is there something that is going to form a precipitate? Is there any combination of a cation and anion that will form a precipitate? And we will see that, well, nickel nitrate, no, that's not going to form a precipitate. Nickel hydroxide, if we come over here, well, hydroxides, let me come over here. So hydroxides right there are usually insoluble, and nickel is not an exception. So nickel hydroxide should be our precipitate. So we'll come back over here and let's write out this equation. So we'll put nickel NO3 2 AQ, all right, plus, and we will need to put coefficients in front of some of these, plus sodium hydroxide, so NaOH AQ. And then I usually write my precipitate first, and the precipitate in this case is nickel 2 plus hydroxide, so that's going to be NiOH 2, and that will be solid. We'll indicate that with an S. And then finally for the other one, we're going to have the sodium ion and the nitrate ion. It's the stuff that's left over. And so that will be NaNO3 AQ. Since sodium's +1, nitrate's -1, that is the formula. All right, if we look at this, we will see that this is not balanced, so we'll go ahead and balance it. Nickel is our largest element here, so there's one there, so I'm going to lock those in place by putting a 1 out front. And then sodium, I think, is our next biggest, but sodium doesn't really work here, so we're going to do nitrogen. All right, oxygens and everything, so we want to save that for last. So let's do nitrogen. And if we look here, we've got 1 times 2 times 1, so that's 2 nitrogens there. To get 2 nitrogens out of this, we'll put a 2 out front of that sodium nitrate. And now let's go ahead and do sodium. We've got 2 sodiums here, so we'll put a 2 in front of the sodium hydroxide on that one. Okay, so there we go. That is our first one. So next, let's look at the ions. So we can already recognize these. So sodium hydroxide, and then potassium is in group 1, so it's K+. And then sulfate is SO4 2-. And we're looking for any combination of a cation and anion that gives us an insoluble compound. So if we come over here, we'll find that, well, sodium hydroxide, well, according to our rules, sodium is soluble. Sodium sulfate, well, sodium is soluble. Potassium hydroxide, well, potassium is in group 1, it's soluble. Potassium sulfate, it's soluble. All of these are soluble. So for this, we're going to have no reaction. So we will have no reaction. When we mix these solutions together, we'll find that everything stays in solution. So that one's pretty easy. All right, next, let's look at this one. We've got sodium sulfide and copper acetate. And so we've got sodium is +1 and sulfide is 2-. Copper here, well, acetate, we know, if we look over here, we'll see that acetate is got a -1 charge. So that means that the copper must be 2+. And then the acetate is C2H3O2-. All right, and when we look, is there any combination of a cation and anion? Well, sodium, we can neglect that one because sodium is always soluble. It's on the always soluble list right in here. So sodium sulfide and sodium acetate are definitely going to be soluble. Copper sulfide, that looks like a good choice for insoluble. We'll see that sulfides are usually insoluble, and copper is not an exception. Don't confuse calcium there. Calcium is something different. So we can now write what our equation is going to be. So we've got the sodium sulfide, NaSAQ. Oh, I need to put that 2 there. So Na2SAQ. And then for the copper 2 acetate, so Cu, C2H3O2, 2AQ. And then on our product side, our precipitate, we decided, is going to be the copper 2 sulfide, so CuS solid. And then our other compound is going to be sodium and acetate. So it's the things that didn't precipitate are going to be what's left over. Sodium's +1, acetate is -1. So the formula for that is going to be NaC2H3O2AQ. All right. Now, technically, these equations are not correct unless you put the states. So make sure you put the states in there. Before we can declare victory over this, we need to check if it's balanced. It is not quite balanced. Copper is our biggest element, so we've got 1 there, 1 there. We'll lock those coppers in place by putting a 1 in front of each of those. Sulfur is our next biggest element, so we've got 1 sulfur here. There's 1 sulfur there, so we'll lock the sulfurs in place. So sulfur's balanced. Now sodium, we've got 2 sodiums here. We've only got 1 there, so we're going to put a 2 in front of the sodium acetate. If you go through and check everything, you will now see that this is a balanced molecular equation. Okay, so now that we have done that, I'm going to go back over to the presentation. All right, and we want to look at the concept of the complete ionic equation. The complete ionic equation is where we take anything that is a strong electrolyte and we dissociate it. What that means is that we will write the ions with the letters AQ beside them to indicate that those ions are dissociated, that they are free to move about independent of their other ions. So we're going to dissociate anything that is a strong electrolyte. Well, that means that we need to recognize what our strong electrolytes are here. So anything that's a soluble ionic compound counts as a strong electrolyte. Well, if you've done this correctly up here, then if it's an ionic compound and it says AQ, it must be a strong electrolyte. So this is going to be a strong electrolyte. Potassium chloride is a strong electrolyte, so we'll dissociate this. If it's a solid, we're going to leave it. So we do not precipitate, or since it formed a precipitate, we are not going to dissociate it when we write out our complete ionic equation. And then here for potassium nitrate, well, this will dissociate. It is a soluble ionic compound. In order to do this, it really, really helps if you know your polyatomic ions. So make sure that you get those polyatomic ions down. So here, when we dissociate this, we're going to get a silver ion. And it says Ag plus AQ. Again, when you see an ion that has AQ by it like this, that indicates that that ion is solvated by water and is free to move around independent of its anion. And this anion, the same thing, it's free to move around independent of the silver cation. So nitrate, and then here potassium, we've got 1 potassium ion, 1 chloride ion. Silver chloride, we don't dissociate it because it is the solid that's formed. And then for potassium nitrate, potassium is dissociated and the nitrate is dissociated. All right, so that is our complete ionic equation. This tells us everything that's in solution. So the complete ionic equation is a really useful tool. All right. To do our net ionic equation, it's really easy. If you've done the complete ionic equation correctly, the net ionic equation is going to be a piece of cake. You will cross out any species that are exactly the same on both sides of the equation. All right, exactly the same. We call these things spectator ions, and that's simply because they're kind of watching the reaction. In this case, the spectator ions are not participating in the precipitation, which try to say that a couple of times fast. All right, and then once we've crossed out our spectator ions, we will rewrite what's left over, and that will be our net ionic equation. So our spectator ions here are clearly nitrate is the same on both sides, so we'll cancel those out, and the potassium ions are the same, so we will cancel those out. And what we're left with is Ag plus chloride gives us silver chloride. What's nice about the net ionic equation is that it tells us what changed. It doesn't tell us everything that goes on in solution, but it does tell us what's changed. The other thing that's kind of useful is the things that are spectator ions, it's possible that you could have substituted something else in place of those spectator ions. So instead of potassium chloride, you could have picked sodium chloride, and you would have gotten the same result as far as the precipitation reaction goes. So that's one thing to think about. Okay, so we want to identify our spectator ions. It helps sometimes if you identify them right up front, so you can recognize which things are going to act as spectator ions. If you have an ion that is in the always soluble list, it almost certainly is going to be a spectator ion. If you have something that is in the usually soluble list, it usually is a spectator ion, but not always. Not always. So spectator ions typically fall into these two categories. Now, in the reactions that we're doing right now, we're going to have two spectator ions, but we'll see some reactions later in the chapter that may only have one spectator ion. All right, so let's look at number 23. Again, I'm going to go to that split screen where I have that up, and there we go. So here we just want to name the spectator ions in each of these. Again, we're going to be looking over here in our always soluble list and our usually soluble list. If it's in one of those, it's probably a spectator. Now, again, it's not always, but start with the always soluble list and see if you can find a cation and an anion, and if not, then go to the next list. So for this one, we'll see that sodium is a spectator, because sodium is always soluble, so that's going to be a spectator. And carbonate's not a good bet because it's in the usually insoluble list, but you will see here that sulfate is in the usually soluble list, so it's right here, right? So it's right there. So sulfate is going to be a spectator, and that's it. That's all we're asked to do. All right, so that's all you're asked to do. If you want to figure out what the other things are, and just in case you're curious, let's see, magnesium carbonate is going to be the solid. So MgSO4 is going to be your solid. In case you want to try to write out a molecular equation there. All right, for this one, we've got lead nitrate and sodium sulfide. This one's pretty easy because we've got one from our always soluble list in each of these. Nitrates are always soluble, and sodium compounds are always soluble. So we will put NO3 minus and sodium. Those are always soluble. Okay, so there we go. And in case you're curious, the thing that is going to form the precipitate is lead sulfide. So our precipitate is PbS solid. All right, next here we've got ammonium phosphate and calcium chloride. Well, right away we should recognize that that ammonium ion is going to be a spectator. And over here on this compound, it's going to be the chloride. So chloride ion is going to be our spectator there. And in case you're curious and you want to attempt them, this one is a little bit interesting because of the stoichiometry. We'll find that our precipitate is going to be calcium, so Ca3PO4 2 solid. That would end up being our precipitate if you want to attempt that one. Okay, so we're going to go back and look at the problems. And I've got one more that I want to look at before we tackle these precipitation reactions on number 24. And that is sometimes you'll be given these as word problems, and that means that you will want to be able to do these just based on the word description. So here is the word problem, and I like these because it makes you have to think them through. It says, write the molecular, complete ionic, and net ionic equations for the reaction between ammonium sulfate and lead 2 nitrate. Now, if I'm given a problem like this, usually the very first thing I will do is just to write down the individual ions. Ammonium is NH4 plus, sulfate is SO4 2 minus, lead 2 is Pb 2 plus, and nitrate is NO3 minus. And once we have those, then writing out the other stuff is pretty easy. So we've got ammonium sulfate. Well, ammonium is, ammonium is +1, sulfate is -2. That means the formula for ammonium sulfate is going to be NH4 parentheses 2 SO4. And then for nitrate, it will be Pb parentheses NO3 close parentheses 2. All right, and those will both be in solution. Now, for determining what is going to form a precipitate, well, the precipitate is going to come from the things that are insoluble here, and as we see here, lead sulfate ends up being on our insoluble list. Sulfates are usually soluble. However, lead 2 sulfate is insoluble. So we can identify what our precipitate is going to be simply by, we can identify the precipitate by looking at our solubility rules. And by the way, I should probably mention this. These solubility rules, when I took chemistry, I had to memorize them, and I have them permanently memorized. I've forgotten all kinds of other stuff, but I remember these. What we have done is that we have taken these solubility rules and pasted them into the instructions of the test. Since you're taking your test on the computer, you'll just go up and look at the instructions and you will see these solubility rules. You're welcome. All right, so back to the problem here. So PbSO4 will be a solid. And then ammonium nitrate will be the other compound that stays in solution. So that is our molecular equation. Now, if we look, this is not balanced. Let's pick our biggest element. Our biggest element is lead. So we're going to lock these 2 leads in place. So there's 1 lead there, 1 lead there. We'll lock those in place by putting 1s in those. Our next biggest element is sulfur. We've got 1 here and 1 over here. So we'll lock this in place by putting a 1 there. And then finally, let's look at, we've got nitrogen in multiple places. Let's do hydrogen. So 1 times 2 times 4, that's 8 hydrogens there. To get 8 hydrogens out of this, we would multiply this by 2. If you go through and check all your elements, you will now see that this is a balanced molecular equation. All right, this will be much easier if you have your polyatomic ions down. And by down, I mean know your charges, know the number of other ions, all that stuff. All right, so get your polyatomic ions down. So next, from our molecular equation, we're going to go on to the complete ionic equation. So here is our molecular equation. Okay, when you dissociate any strong electrolytes, pay attention to the number of ions that are present. And this can get a little bit tricky. So here, we'll dissociate anything that is a soluble ionic compound, and that's going to include all of these ionic compounds that are AQ. So this is a strong electrolyte, as is lead nitrate. Lead sulfate is not, because it's a solid. And then the 2 ammonium nitrates, that is also a strong electrolyte. So here we're going to have 2 of the ammoniums because of this 2. And those 2 ammoniums will move around independent of each other. So we're going to write it like this. So we'll put 2 ammonium ions. We'll have the 1 sulfate ion that has a 2- charge. The lead 2 ion will be an ion. And then we're going to have 2 of those nitrate ions. For this one, the lead sulfate, we're going to leave that together. And then this, kind of think of it like the distributive property. When you're multiplying, we're going to have 2 ammoniums and 2 nitrates. So 2 ammoniums and 2 nitrates. So that is our complete ionic equation. Now, whenever you're doing this, your complete ionic equation, you could go through and double check to make sure everything is still balanced. That will help you to find any mistakes of forgetting to pay attention to those parentheses and stuff. But if you do it right, then everything should still be balanced. So now we've got our complete ionic equation. We want to get our net ionic equation. And the way to get the net ionic equation is simply to take anything that is on both sides and cross it out. So we'll cross out our spectator ions. So our spectator ions here are going to include, let's see, ammonium. So we'll cross out the ammonium ions and the nitrate ions. They will cancel out. And then what's left over is our net ionic equation. And again, the net ionic equation tells us just what changes. All right, so let's look at number 24. I'm going to go back to our vertical split screen here. All right, we're going to do number 24. So when I've got problems like this, where I've got the compounds that we're starting with, I like to write the ions directly underneath. So I like to identify what the ions that we're working with are going to be. So here are ions that we are working with. Well, this is chromium, and you can tell by the charges here that chromium must have a 3+ charge. So we're going to have chromium 3+. Sulfate is SO4 2-. Ammonium, as you have learned, is NH4+. And carbonate, as you have memorized, is CO3 2-. And we want to look at our solubility rules here to determine, are we going to have a precipitate? And the answer is yes. Ammonium and sulfate end up being spectator ions here, but the chromium and the carbonate should form a precipitate. If we go back over to our rules here, let's see, carbonates are usually insoluble, okay? And we will see that chromium is not an exception. Now, of course, ammonium is an exception, which is why we were able to have that ammonium carbonate to begin with, but the chromium carbonate is not an exception. All right, so now that we know that, let's write the formula for chromium carbonate. So chromium is 3+, and the carbonate is 2-. And if we do the crossover thing, we're going to get Cr2, CO3, 3, solid. And then our other compound is ammonium sulfate. Ammonium's +1, sulfate is 2-. So our formula for that is going to be NH4 2 not CO3, SO4. All right, I clearly didn't leave enough room in there, so I'm just going to write it up top here, or write it down below. So NH4 2 SO4 AQ. Now, before we can move on, we do need to balance this. And chromium is our biggest element here. So since chromium is the biggest element, we have 2 there, 2 there. We'll go ahead and put a 1 to lock those chromiums in place. Next, why don't we look at sulfur? So sulfur, we've got 1 times 3 times 1. That's 3 sulfurs there. To get 3 out of this, we'll put a 3 here. And then finally, we can look at nitrogen. Nitrogen, we've got 3 times 2 times 1. That's 6 nitrogens there. So to get 6 nitrogens out of this, we will put a 3 in front there. And that gives us a balanced molecular formula. Now, to do the complete ionic equation, we need to take anything that is a strong electrolyte and dissociate it. So we're going to dissociate this. So we'll do this. So this chromium sulfate, that is a strong electrolyte because it says AQ. It's soluble. Same here. This one is not a strong electrolyte, and this one is a strong electrolyte. I think the trickiest part about this one is paying attention to all of the coefficients and those subscripts, and remembering to write your charges, and then remembering to write the states. So for chromium, we're going to end up with 2 chromium, 3 plus AQ, and 3 of the sulfates, so 3 SO4, 2 minus AQ, and then 3 times 2, so that's going to be 6 ammonium, AQ, and 3 carbonates, so 3 CO3, 2 minus AQ, and then this, we leave it together, so Cr2, CO3, 3, solid, and ammonium, 3 times 2, so there's 6 NH4 plus AQ, and I'll have to write this down here, 3 sulfates, so 3 SO4, 2 minus AQ. So that's a lot to write, but it's not too bad. And now we want to cancel out any spectator ions. So we'll cancel out, we've got 3 sulfates on each side and 6 ammoniums on each side. And what's left over is our net ionic equation. So we'll put 2 Cr 3 plus AQ plus 3 CO3. So 3 CO3, 2 minus AQ, and our product Cr2 C. So CO3, 3 solid. Okay, so next, let's look at the ions that are in this problem. So barium is in group 2, so we have Ba2 plus. Nitrate, of course, is NO3 minus. Potassium is in group 1, so K plus. And sulfate is SO4 2 minus. Now you'll see nitrate and potassium are always soluble, so that means those are probably not going to be the precipitates. And so our best bet is with barium sulfate. If we come back over here to our list, we'll see that sulfates are usually soluble. However, barium is one of the exceptions. So our product here, one of our products is going to be barium sulfate. So we will put Ba, and barium's 2 plus, sulfate's 2 minus, so it'll simply be BaSO4 solid. As far as the other compound, it comes from potassium and nitrate. Potassium's +1, nitrate is -1, and so that will simply be KNO3 AQ. So now let's balance it. Barium is our biggest element here, so we'll balance the barium first. We've got 1 there and 1 there, so we'll lock those in place by putting a 1. Our next biggest element is potassium. However, potassium isn't locked into place anywhere, so let's do sulfur. Sulfur, we've got 1 sulfur here. We can now lock this in place by putting a 1 in front of it. And now let's do potassium. With 2 potassiums there, we can balance it by putting a 2 in front of the potassium nitrate. If we go through and check, we will see that everything else is balanced. So everything else is balanced. So now what we want to do is we want to write the complete ionic equation. So we'll dissociate anything that is a strong electrolyte. Well, barium nitrate, that is a strong electrolyte. It's a soluble ionic compound. Potassium sulfate, soluble ionic compound. It's a strong electrolyte. Barium sulfate, no, not a strong electrolyte because it's a solid. And then potassium nitrate, yes, that is a strong electrolyte because it is a soluble ionic compound. So now let's dissociate those 3 things that we found that were soluble ionic compounds. So we've got barium 2 plus AQ plus 2 NO3 minus AQ plus 2 potassium ion AQ plus sulfate 2 minus AQ. All right, for the barium sulfate, we'll leave that together. So BaSO4 solid. And then we have to distribute that 2. So we'll do 2 potassium ions AQ and 2 nitrate ions AQ. All right, we'll cancel out anything that is the same on both sides. We'll see that we have 2 nitrates on each side and 2 potassiums on each side. So what's left over is our net ionic equation. So that will give us barium 2 plus AQ plus SO4 2 minus AQ, and then that gives us BaSO4 solid. All right, we've got one more left, and then we're going to end this video. So here we've got iron nitrate, and you can tell by that 2 that this must be iron 2. So Fe2 plus, and then the nitrate, of course, is NO3 minus. For potassium, of course, it is +1, and hydroxide is -1. When we come over here and look at our solubility rules, we'll find that, of course, nitrate and potassium are probably spectators. So our best bet is going to be iron with hydroxide. And if we come over here, we'll see that hydroxides are usually insoluble, and iron 2 is not an exception. So first things, let's write the formula for the iron 2 hydroxide. So we'll put FeOH2 solid. All right, and then the other compound is potassium nitrate. So we'll put plus KNO3AQ. Before we can do the complete ionic equation, of course, we need to make sure that it is balanced. We'll start with iron, since iron is the biggest element here. So Fe, there's 1 here and 1 there. We'll lock those 1s in place by putting those there. Potassium is our next biggest element, but it's not locked in place, so we're going to do nitrogen. Nitrogen, we have 1 times 2 times 1. That's 2 nitrogens here. To get 2 nitrogens out of this, we will put a 2 in front of the potassium nitrate. Now let's do the potassium. We've got 2 potassiums here. We'll put a 2 in front of potassium hydroxide. If you go through and check now, you will see that everything is balanced. We want to dissociate to get to the complete ionic equation. We want to dissociate everything that is a strong electrolyte. So we'll dissociate this one, strong electrolyte, this one, not this one because it's a solid, and then we will dissociate this one. All right, so iron 2, we have Fe2 plus AQ. We have 2 of the nitrates, so 2 NO3 minus AQ. We have 2 potassiums, so 2K plus AQ, and 2 hydroxides, AQ. On the product side, we've got FeOH2, so FeOH2 solid. And again, we're not dissociating that one because it is a solid. And then here we've got 2 potassium, so 2K plus AQ and 2 NO3 minus AQ. So that is our complete ionic equation. And next, we want to get our net ionic equation. And to get that, we want to cross out anything that is identical on both sides. Well, we've got 2 nitrates here and 2 potassiums there. And that leaves us with Fe2 plus AQ plus 2 hydroxides AQ, and that gives us FeOH2 solid. Okay, well, that is the end of that particular section. So we're going to stop the video. We'll go back over here and we'll see that the next section is we're going to look at acids and bases, and that is section 4.3. So that will be on the next video.